Very welcome to this webinar where we will tell you about the use of technology to ultra clean air and how we can reduce airborne contaminants in healthcare environments. My name is Peter Hojeback. I am CEO of Avidicare, a Swedish-based company. Let me start by saying we have participants here from several places in the US that are joining us from different parts. Many of you are engaged in hospital engineering. I will start to share my screen with you as well for today's webinar. Right, so for today, what's on the agenda? Well, first of all, we start by going through some recent developments in airborne contamination risks. Then we'll spend some time looking at different solutions, how you can reduce airborne contaminants in operating rooms especially. And finally, we go through temperature-controlled airflow technology, which is an alternative to the traditional ventilation systems you find in most operating rooms around the world. Now, why at all bother about airborne contamination in operating rooms? Well, of course, because these extremely troublesome surgical site infections can happen to anyone, because all of us may one day need surgery. It could be ourselves, our kids, our parents, our families, or our friends. And anybody is susceptible. When you open up the skin and you start doing surgery, you're exposed to infections, especially these surgical site infections that are actually horrible, deadly. So that's why our company, Avidicare, we have a motto that we are here to help healthcare work towards zero infection, because that is the only realistic goal, and that is what we all hope to achieve. Because nobody, of course, wants to become ill in hospital. Now, the status for surgical site infection is actually a problem that is getting worse and worse. The CDC in the US reports about 1.9% surgical site infections, but many medical centers report much higher values. We have one example of a US cancer center that has 12% surgical site infections. The total number is roughly 300,000 in the United States each year. And if you do get a surgical site infection, your risk of dying is between 2 and 11 times higher than if you had not gotten the infection. Now, the number of actual infections may be, or probably is, much larger than this 1.9%, which is sort of the official rate. Within the Veterans Administration, they did a big study, about 600,000 patients. They studied how many people do get surgical site infections. Their previous value was 3%, but that was after 30 days. They also looked now after 365 days, and they found it was twice. So it's about 6% is more the actual number of patients who do get surgical site infections. So it's a problem that can happen way after the first month after surgery. Still, most hospitals say that, well, our rates of infections are going down. Sure, that is true for most kind of infections, but not the surgical site infections, at least not according to the official quality registers of the CDC. They found no reduction in surgical site infections between 2014 and 2018. At the same time, the most susceptible surgeries are when you are replacing your hips or your knees. That is also kind of surgery that will become much more common, because as we're getting older, we want to remain active. We want to keep walking. We want to keep riding a bike. We want to keep playing golf. We want to be as active as we were when we were younger. And then many of us will need new hips and knees. So there are projections of much higher rates of hip and knee replacements over the coming years. And another worrying fact is that the antibiotics we are using are getting more and more susceptible, and the bacteria are they're getting less effective, and bacteria are increasingly resistant to these antibiotics. So relying on antibiotics as a strategy to fight surgical site infection is no longer valid, It's much better to make sure that the bacteria don't get into the wound in the first place. This actually has triggered the WHO to say that we got to prepare for the post-antibiotic era. Now, what does science tell us about airborne contaminations? Well, what we do know for sure is that if you have more bacteria in the air, you are more likely to have an infection. That's sort of super obvious. If you have zero bacteria in the air, you have no chance of getting infection from the air. Whereas if you have billions of bacteria in the air, the likelihood of getting infection from the air is of course way higher. And now in terms of COVID-19, we all know that the air can carry many different contaminants, short distances or further on. The pioneers of orthopedic surgery, the guy who invented the big hip implants and knee implants, is Sir John Charnley. He found out when he did research and when he did his surgery that he had very high rates of surgical site infections, almost 10%, 8.5, suffered from infection. But what he did was he tried to clean the air in different ways. And he made sure that if he could reduce the number of bacteria during surgery from around 600 CFUs per cubic meter of air, a CFU is a colony forming unit, about from 600 down to less than 1. He was able to do that just with clean air and more air changes and better clothing. He reduced the surgical site infections to below 1%. And he found that for more than 6,000 patients he had in his studies. Still, it was only one guy in one hospital. He did that, of course, for quite a long time. But we needed to find out, is this really true? So there was another team of scientists under a guy called Lidwell. They did in 93 perform a study for 19 hospitals in 3 countries and more than 8,000 patients, where it was fully randomized and a prospective and multi-center study. And they did find out that yes, ultra clean air does really bring down the number of surgical site infection, as does better clothing and as does antibiotics. They also found out when they looked at washouts from the wounds that they could trace the bacteria in the wounds, in the surgical site infections, back to the skin of the staff. And they could find out that they had been carried to the wound via the air, either directly or onto the instrument table and then via the instruments into the wound. They defined in that study that the level you need to aim for and what you want to achieve is to have less than 10 colony forming units per cubic meter of air. That's the design goal. That's what you want to be, and that's what you should measure in your operating room to make sure you have as low risk of infection as possible. And of course, as you probably all know already, the staff is the main problem. It's the skin of the staff. People are shedding bacteria all the time. And as we are hot, the air rises upwards, and with it, it carries like a cloud of bacteria. And this is what we really want to make sure that this cloud of bacteria is swept down and away from both the wound and the instruments. What we have learned from COVID-19 is that not only is this a problem for during surgery for infections, it's also a very big problem for healthcare in general that the air isn't clean enough. We have seen in the US a huge amount of contaminations and one of the highest rates of deaths globally. We know one of the really exposed groups of people in society are healthcare workers. The CDC has tracked those initially, but they stopped doing that in May. But we do know that during the fall, there were about 900 healthcare workers in a database from Kaiser Family News that they were tracking, and there were probable cases of COVID-19 deaths among healthcare workers. In UK, they have reported that 1 in 10 dead are healthcare workers. Now, with the growing recognition that SARS-CoV-2 is also airborne, the WHO has revised its guidance. And there is evidence that also of long-range transmission. It's not only droplets that carry 4, 5, 6 feet. That you're also able to find viable viruses in the air for much longer time in the air. And there are several such studies around. It is still debated, and it seems that the main pathway to contamination is contact, that these droplets fall onto the floor or to tables or places where you put your hand, and then you put your hand into your face somewhere, and that's the main pathway. But there is also a pathway. And what is fully agreed among experts is that we do need better ventilation to minimize the risk of airborne contamination. I would say that this is actually quite troublesome if you're working within healthcare and you go to your job, and every day you're really worried of getting these infections that might kill you. And we are finding that the sort of psychological safety is going down, and healthcare workers are really worried. So we could do better. We can do better. A further complication of COVID-19 is that business is closing, and by business I mean hospitals, clinics. They have stopped elective surgery in many cases. And that is also, of course, a financial problem, because surgery, that's sort of the financial engine of most healthcare facilities. So the financial consequences are huge, and there are figures from AHA that the losses is about $50 billion a month. That was during the spring. So these losses are, of course, horrendous, and many businesses have been forced to close. It has also created a huge backlog of surgery, and if you're not allowed to do the surgery, not get your hips or your knees replaced that you have been longing for a long time, that of course creates a lot of pain as well, and unnecessary pain. And still today, many people are hesitant to go to the dentist or to have surgery performed on them, even if it's plastic surgery, or even going to the dentist is a concern right now. So as facilities, we should work to make sure that our facilities are kept as safe as possible, both for patients and for staff. Now, what tools do we have? What solutions do we have to reduce the risk of airborne contamination? Well, we need to look at these ventilation systems with a couple of questions in mind. Are they good enough? Based on what I've shared just now, are they good enough to keep surgical site infection rates low? Are they good enough to keep staff safe at work? Are they good enough to keep hospitals open? Well, obviously, there's a big question mark here. And that's why these current technologies are challenged. They're basically not delivering. They're not doing the job they're supposed to do. Not good enough, at least. The two types of ventilation you are using in hospitals, especially in operating rooms, is either the turbulent mixing ventilation or laminar airflow, or protected zone system, sometimes called unidirectional airflow as well. These two technologies, I'll share a bit about each of them. The turbulent mixing ventilation relies on dilution. It's roughly just about air changes. You put in as much air as you can, you try to mix it as much as possible so you don't get any stagnant zones. You are designing often with a number of people and the clothing concept in mind in several countries, mostly in Europe. In the US, not that often. However, research has shown that these ultra clean conditions that we want to achieve to minimize the risk of surgical site infections, you're not able to reach those levels unless staff wears ultra tight clothing. And tight, I mean clothing that doesn't allow for any of these particles that staff is shedding to enter into the air, or just very, very small rates. And they also claim that to have ultra clean conditions in a mixed ventilation operating room, you need to restrict movement. Absolutely no unnecessary movements in that room. So both restricted movements and tight clothing are required to keep it ultra clean. But even if you do that by just doing 20 air changes mixing, you do not reach it. Even if you go up to 60 air changes, you're still not reaching ultra clean conditions in your operating room unless you also add the ultra tight clothing to that. And the challenge is, of course, ultra tight clothing are not comfortable. They are, to many in staff, really reacting hard to it. It's sweaty, And some of them are getting rashes, eczema, even fungi. And I would say, as a scientist here in this, or engineer, that's is this actually future proof? Is this the best we can do to mix ventilation? This is really, even from a theoretical point of view, the least efficient system of any imaginable. You can't do it less efficiently. That means that efficiency only scales linearly. That means if you want to cut down the number of bacteria to half, or you want to improve, you want to have twice as many people in the room, you need to double up on airflow. So it doesn't scale well. And let's just presume that now we're building a hospital, an operating room that's going to last for the next 20 or 30 years. And we do think that antibiotic and the antimicrobial resistance is increasing quite significantly over the years. So it's not at all unlikely that we will need to have cleaner air. And if we then start with mixing ventilation, we have nowhere more to go. Now, the more common when it comes to infection-sensitive surgery is laminar airflow. Laminar flow, unidirectional flow, both systems, or both names of systems, work on the principle of creating a protected zone. That's one area of the room that is kept really clean. This is a tradition from clean rooms. I mean, industrial clean rooms where you're manufacturing food or pharmaceuticals or semiconductors, stuff like that. The way to design them in most parts of the world is that you start by assessing how much space do you need for the surgical activities. Your ultra clean zone, how big does it need to be? You need to have all your instruments, your implants, the patient, the surgical team must be fitted within this zone. Then you're adding diffusers in the ceiling that is larger than that zone to cover that area. Of course, in the US, you have fixed areas that you need to have instead. Then in many countries, you test if it works by doing an entrainment test. You are releasing lots of particles in the periphery and see whether they penetrate into the middle, or at least not too many of them are allowed to do that. And if you can create this sort of virtual wall between the periphery and the protective zone, then you're okay. The challenge of this thinking is that this is a clean room thinking. In clean rooms, people are working very slowly, and they can really be dressed in super tight clothing as well. It doesn't matter. They're not as actively working. And here, furthermore, we have this staff that needs to have different clothing system that is super active, that really moves a lot. If you've ever been into an operating room where they're performing orthopedic surgery, you do know for sure that it's very highly active and people are sweating and working a lot and generating lots of particles and shedding lots of bacteria from their skin. So this is the design. It's often designed to ensure a certain speed at table height, of course. When we are talking about laminar airflow systems, we should note that scientists are looking at a laminar airflow in US setting, US operating rooms. The air isn't moving in a laminar fashion. It's actually, since it's only 20 air changes usually, started to become turbulent quite quickly. So you can discuss whether that is actually laminar airflow. And you can compare this to many countries in Europe where a laminar airflow needs to have about 60 air changes, much higher airspeed in order for the air to remain laminar also when it hits the operating table and not become turbulent before it reaches the operating table. And in the US, of course, there is no validation of this critical zone in the way that's done in some other parts of the world. Now, a little bit of entertainment. This is a smoke test. This is just a person standing, normal body heat. We're releasing some smoke on the floor. And you can see just because the person is warm, the air is moving upwards. And this air is, of course, the cloud of bacteria that is being released by the staff. So you can see that this is something we don't want to have. We don't want all these bacteria to start circulating up into the room. We want to remove them and sweep them away from the operating table and the instruments. To do that, to counteract this warm air rising, you need to have a certain speed of the air. And science shows us that about 0.3 meter per second is required as a speed to ensure that it's actually efficiently swept downwards. We are seeing that if you do it correctly, you're able with the UDF to create that powerful downflow in a laminar flow system in the protected zone. However, if you go outside the protected zone, you are way above the 10 CFU level you need for ultra clean conditions. So a laminar flow system, protected zone system works quite well in the middle, whereas as soon as you're leaving the protected zone in the middle, there's a lot of airborne contamination. This has actually caused the WHO not to recommend laminar flow systems anymore, since it leaves the other parts of the room dirty. And that is mostly because the instrument tables are not within that zone as they are supposed to be, because surgery is hectic, things are going on, and especially if you have a smaller laminar flow system, the area is just plainly too small. There was a study in the Netherlands where they checked out during surgery, for how long time is all the equipment and all the staff within the protected zone. So they checked at first in the operating room, and they found out prior to doing any markings on the floor that about during 6.1% of the time, everything was in the right spot in the protected zone. Then they started doing education, and they also made these markings on the floor. You can see here the red marking on the floor in a zone. And if they did that, compliance rose and to between 36 and 52% of the time. That still means that even if you do marking, even if you educate, the risk of having your instrument in dirty air is quite high in a laminar flow system. So this is probably one of the main reasons why the WHO and many studies cannot see any advantages, any better outcomes of using laminar flow. So it actually does not recommend any laminar flow systems anymore. And to make it even worse, if you're having more complicated surgery and you have multiple staffs in the room, then you would need a really, really big laminar flow system, maybe like 12 by 12, or you could even by 16 by 16 feet. And that would require enormous amounts of air. So that is actually not very sustainable. And this has been confirmed by several different computer fluid dynamics studies also, that this is a challenge for laminar flow systems. It's just clean in the middle. So then we need to ask ourselves, with these two systems, are we okay with having just them? These two systems do have huge challenges to deliver better outcomes. The outcomes we have today, they are obviously deadly and expensive. Will things improve by themselves? Well, not likely. The need for clean surgery is rather increasing. And at the same time, antibiotics are losing their powers. Can we really, is it okay just to wait and see what happens? No. We would say there is a true need for innovation. This we can do so much better than what we currently are doing. And that's the whole rationale why Avidicare invented the technology of temperature-controlled airflow. That's as a better alternative to the current two ventilation systems. The goal here would, of course, then be to minimize the number of airborne bacteria and viruses, and at the same time provide really excellent comfort in the room for the staff, and at the same time use as little energy as possible. 3 goals for designing temperature-controlled airflow system. Now, what is it? Well, it's like a combination of the two other technologies. You can see that in the periphery, this is the orange part here in the middle. You are having a mixing system or an improved version of mixing system. And in the middle, you're having a unidirectional airflow. But it's not any unidirectional airflow. It's an improved version of unidirectional airflow. And the trick here is that we're using gravity as the force to drive the downflow, not the power of the fan. So with this UDF in the center, we are releasing HEPA-filtered air in this ring. You can see a similar ring above my head here of air showers, or you call them diffusers. These are low impulse laminar flow diffusers mounted on this central unit. The downflow is created by having a 2 Kelvin. It's about 2 centigrade, or in this range about 3 degree Fahrenheit, lower temperature than room temperature. So the difference in temperature is between the temperature in the room as measured at table height on the walls, and this gravity, this cold air. I mean, cold air is of course heavier than warm, so it will fall down by itself. It will actually accelerate, just like if you're dropping a ball, it will fall faster and faster, and the air will actually fall faster and faster and have a very powerful and super quiet downflow compared to downflow from a fan. You're actually more resilient and robust also to any obstacles in the downflow, which is a major concern if you're using laminar airflow, that you're getting too much turbulence below lamps and other obstacles. In the periphery, we have mixing ventilation, where we again are supplying HEPA filtered air that is sort of fed in the periphery, and that makes sure that the air that's being falling down in the middle doesn't whirl back along the walls and get back up again and recontaminate any instruments or get back into the clean zone in the middle. So this is a very efficient way of pressing down the air to the floor and making sure that all air moves downwards. This system is also the system that controls temperature of the room. So if the room is too cold and the staff wants to have it warmer, it will supply a little bit warmer in the periphery, and in that way ensure that the whole room temperature goes up. Or if the staff wants to have it colder in the room, in the periphery you will provide the same temperatures in the middle, which is colder than room temperature. So that will mean the temperature in the room will go down. So it's basically two control systems in the same room. This means that the staff can set any temperature they like. They can have it really cold for hypothermia patients, or they can have it really warm if they are working on heart surgery for small children, for instance. We have installations in all these different scenarios. And since we're supplying temperature, we can supply temperature for both zones. We can change the room temperature extremely quickly. That means faster operations and shorter wait time in between surgeries. Now let's dive a bit more into how it works. You can see here in this 3D picture, the central supply is the inner zone. That is the one that having the temperature that is 2 degrees Kelvin colder than the room temperature. And since that air is cold, it will fall down. Then it exits the room in the 4 low corners where we have the exhaust, just as ASHRAE prescribes. In the periphery, we are releasing also clean air, but at somewhat warmer temperature usually. So you can see how these two zones are created in the room. This means that in the inner zone, you're having less than 5 colony forming units per cubic meter of air, which is well below the threshold of ultra clean surgery. And you have, even in the periphery, below 10 CFUs. Now, this is just an example here what it looks like from a technical point of view. This is on top of a room. This is just an example where there's one air handler for this room, but of course the supply can come from huge air handlers in a bigger hospital instead of in this. So this is just an example. You can see here that it's the air, you get some fresh outside air. The amount is, of course, you can have any amount that your local regulations require. The air is fed through a pre-filter. Then the air is conditioned by a cooler and heater. Then you have your fan, and you have a secondary filter. What then happens is that the air is split into 2 ducts. One duct that is going straight, in this case, to feed the center. This is passing through a cooler, because this is supposed to be a little bit colder, or at the same temperature as the periphery. And in the periphery, you're supplying, in this case, it's actually divided into 2, but then you're supplying the peripheral air here. In both cases, you have HEPA filters before the air enters the room. Of course, it's not a requirement as such to have HEPA filters. You can have other filters than HEPA filters if that is what your local regulations require, though many prefer to use HEPA filters. The air is then pushed down to the floor and exhausted at the four low corners of the room. Then all that air can be either exhausted or it can be recirculated. So we have some customers, some hospitals that are recirculating or more or less all air, whereas others are not recirculating any at all. So that is totally optional and can be configured according to the needs of the hospital. We are also having similar installation for prep rooms. In this case, there is a prep room where we're opening up all your instruments and preparing the surgery, which can be adjacent in an adjacent room to the operating room, of course. And it works very similar to the first one, although in these cases it's often not 4 exhausts, it can be fewer. This central part, the central opragon, is stainless steel metal. It's about 2 meters or 6 feet in diameter. It's about a foot high and about half a foot sticking down below the inner ceiling. It attaches to the duct working anyway. We can have circular duct connections, we can have rectangular ones. It can be supplied from the side or it can be supplied from the top. If you have a refurbishment, it's often very difficult to, you may have very constrained space between the hard ceiling and the inner ceiling. So, but we do need at least a foot. That is the distance that is required by the opragon, but that is way less than any laminar flow system would require. So if you have a tight installation, it could be an old building, an opragon can be the solution for you here. The peripheral part, if you make a cut through, you can see what it looks like. You can make a cut out in the center if you want to have pendants for lamps, for instance. You can have that in the middle. You can see how the air showers are attaching. You can see the flange here where you can rest the inner ceiling. And here are the mounts that you're then affixing to the firm ceiling. And these are the air showers. They're made out of balprene. These are the diffusers. Now, how does it compare? What does it look like? Well, the challenge is you can't see air and you can't see bacteria in the air. So we got to use technology here to show how the air is moving. And the Institute of Technology in Stockholm, they're ranked in the top 100 universities in the world, and they have one of the most powerful supercomputers in Northern Europe. They do these simulations together with us. Here you can see on the left-hand side an operating room. You see the staff standing here. You see the table. You can see the air is from the side. You can see the air being rushed down under a laminar airflow system. And you can see how the air is pushed down. The protective zone in the middle is kept very clean. And all the bacteria are pushed down to the floor. But then because of the airflow, it also rushes up and creates this vortice. And here, of course, all your bacteria are gathering. And if you can imagine, of course, if you were to have an instrument table here, just behind the back of the surgical staff, that is quite likely that bacteria enter and deposit onto those instrument tables. Compare that with temperature-controlled airflow. Here you can see in the middle, you are just as with the laminar airflow system, having a unidirectional airflow, quite a powerful one even below obstacles. Here you see some lamps, that it keeps sweeping. The downward motion is actually very powerful because gravity provides that sweeping effect. It's not turbulence, and it's not the impulse from the fan. You can see here that in the periphery, these vortices, of course, they will also happen in temperature-controlled airflow, but as the ultra-clean air that's being pushed down, the HEPA-filtered air is being pushed down here as well, these vortices are suppressed and kept low to the floor and below the height of the operating table and instrument tables. So this means that you are able to create ultra-clean working space in the whole room. The whole room is a place where you can work, not only the protected zone. So that is a huge advantage for staff that can work in a much more efficient way than otherwise. This is just an example showing what happens. These dummies are hot, the guy is warm, but all bacteria are effectively pushed down. This is an Opragon temperature controlled airflow system that is operational. Now I'm talking about these vortices in the periphery. Here to the left you can see that the air that's pushed to the side in the laminar airflow system does rise along the walls. You can see how it circulates back into the room, creating this vortex that you saw on the previous slide. What we also mentioned is you have obstacles in the downflow. Here, when staff is shedding their bacteria, in the laminar airflow system as this one, you can see how all those bacteria gather in the turbulent zone beneath the lamps. And then once there are enough of them, they will deposit and fall down. This is not what you want to achieve. So this is a major challenge. And that's why many lamp manufacturers now are trying to make lamps that are more aerodynamically shaped to minimize this problem. But still, it is a big problem. Compare this with temperature controlled airflow. Here at the bottom, you can see that along the walls in a temperature controlled airflow, yes, the air is still rising, it's going up, but when it comes to this level, it's being pushed down. So this vortex doesn't rise up against the wall and doesn't throw the bacteria back into the room. If you look up to the right here, you can see what happens if you have obstacles. This guy is first testing below the operating table, just making sure, yes, all the air is pushed down as it's supposed to do. Now the tricky test is underneath this. You can see this is a big lamp, it's in the downflow, and compare with the previous video where you saw that all the bacteria gathered upwards and created this cloud. Here, on the other hand, it's being pushed down powerfully. So the lamp is not at all such an obstacle to the downflow as for a laminar airflow system. All right, these are videos, there were CFDs, there were smoke tests, but really the proof of the pudding is the eating, and the proof of if an operating room ventilation system works is if it's able to keep the room ultra clean during surgery with all the staff in the room, because they are the ones shedding the bacteria, they are the ones that are creating the problem. So they need to be in the room when we're checking if the ventilation works or not. We have done that many times. I think we're up over 700 different measurements right now in hospitals all over Northern Europe, actually in the US as well. Very varying conditions, between 2 and 11 people in the room. More than 30 different kinds of surgery have been performed when we were measured. They have been wearing many different kinds of clothing. Most have been using the Opragon 8 system, which is a temperature controlled airflow system. And we're measured in 3 spots in the OR, both by the wound, on the instrument table, and in the periphery of the room. So what we're achieving is that the average around the wound is about 0.4 CFUs per cubic meter, which is very much below the level of ultra clean air that is the requirement. On the instrument tables, we're below 2 CFUs, 1.5 on an average here, which is also very safe. And even in the periphery, where, as you know, with the laminar airflow system is really dirty, we're only getting 4 CFUs. So this is from very, very many different hospitals, many measurement samples. These are what we are achieving. And you can really, if you look at the graphs here, you can almost visualize for yourself how these bacteria are pushed down and away from the wound and out towards the periphery while still being kept low. How is it to work in these conditions? Because we say, yes, we should minimize the number of airborne bacteria and viruses, but we should also make excellent comfort. So another university, Lund University, Lund Institute of Technology, they did research in one hospital that had all these 3 systems installed, same staff, they were in the same hospital, mixing ventilation, laminar airflow ventilation, and temperature controlled airflow. And that research has been published in a journal of hospital infection. And they concluded that the best working environment for the OR team was the temperature controlled airflow. What staff liked was really much that those who are most active, those staff are in the middle, where it's somewhat colder, whereas the people who are more passive and not working as much physically, they're in the periphery, where it's somewhat warmer. So that was a good distribution of temperatures. They also appreciated very much that they didn't have to work in the ultra-tight clothing systems that they had to work in the mixing ventilation system. They appreciated the very low noise. It's actually like that. If you go into a room with temperature controlled airflow, you ask yourself, is it actually operational? So you have to hold out your hands to feel, yes, the air is moving down here. It is running. Or you have to look on a display and see that it's working. And there's no air chill, which is very nice if you're working for several hours. And if you're standing in a strong downflow, that gives drought. So this has been published also. Now, what about the United States? Well, when I visited one of your top hospitals, I shared the presentation similar to this one. And then they asked us, well, okay, that's our averages from Europe. What is it like here for us? They did neurosurgery, and it's actually a super hospital in the US. We measured, we had an independent nurse coming doing the measurements in exactly the same fashion as all the other measurements have been done. The results here was by the wound in the US, you had about 4 CFUs per cubic meter of air. That is luckily below the threshold of ultra clean air. However, by the instrument table, we had 27 CFUs, and in the periphery more than 60. So comparing this to our customers' averages, we're about 10 times higher here, which is a lot. But you then wonder, of course, a lot, yes, how much? Does it matter on outcomes? Well, if you look into the graphs and the study, the really big studies made by Lidwell, you can compare that if you, in a room with our system, you have temperature controlled airflow, you have less than 10 CFU. And if you're just looking at the graph they did, it's a blue line here. Well, if you're in the between 1 and 10, you do it in the middle, you get about 1.2 percent of SSI. If we would say that the US hospitals are between somewhere here in the between 10 and 100, and you find where you are here, you would roughly end up with a 1.8% surgical site infections. So just by installing a better ventilation, we would almost cut the surgical site infection rate in half, everything else being equal from a theoretical point of view. We actually have a hospital that done a similar study, before and after study, with 1,000 patients before and 1,000 after. And they cut their surgical site infection rates from 3% to 1%. So there's also an outcome-based studies for it. Well, just summarizing, it's ultra clean in the whole OR, super comfortable, lowest energy consumption of any ultra clean system, very stable airflow. The air conditioning is integrated in the system. You don't need any heating in the walls or anything like that. Easy to put into installations and very low life cycle cost. But I would like now, following COVID, also address another concern, and that is, of course, protection of staff from airborne contamination. By having this downflow, the likelihood of whatever one person is exhaling is actually being inhaled by another one. If all that air is going down, the likelihood of any infectious transmission is, of course, lower. So instead of just doing mixing, and mixing systems means you want to mix all the air, you want to make sure that everybody breathes everybody else's air. That's the design goal of a system. You're trying to mix it as much as possible. That's not very good from an infection prevention point of view. So we are seeing that using our system can also help out in many other kinds of rooms than in the surgical department, where you want to minimize the risk of infection transmissions. So that means in healthcare, we have many different applications where our technology is installed. Of course, the surgical departments, but also we have installations in the sterile processing department. We have it in hospital labs. We are doing total floors with this technology using temperature control and these dome-shaped diffusers to ensure the cleanliness in the room. We have designed for isolation rooms, and we're actually now proposing them to a couple of hospitals. It looks like this. This is an orthopedic clinic. It's one of the top 10 in the world. They have fantastic outcomes. They just did 7 ORs and 7 prep rooms using our technology. You can see it here. You can see this in the central part, the opragon. You can see the air showers, the diffusers in the periphery as well. And they said that they chose temperature controlled airflow because it created ultra clean condition in the whole OR, which gave the staff much more flexibility. And the surgical team can focus not on the room or where they're supposed to be, but they could focus on the patient instead. So there's another installation also in the Netherlands, 4 ORs, 4 prep rooms, and there was some special configurations for this one. So we're working very closely with that team. The team here at Flevo really appreciated temperature controlled airflow because it was so silent and comfortable. So that was what they appreciated the most, as well as, of course, the flexibility that they can use all parts of the room and not just a square in the middle. We also have temperature controlled airflow systems for hybrids, and this is with you can see the rails in the roof here, and you can see the diffusers fitting here in between the rails. And giving that temperature controlled airflow is much more resilient to obstacles. Whenever you have like this C ring here, C arm that is above the patient, to have a reliable downflow, even when that is in use, is of course a big advantage. Well, this was what I wanted to share with you. This is about temperature controlled airflow. It is a real alternative. We have more than 200 installations in Europe. We have 2 installations, 2 rooms in the United States as well. We are right now offering the technology, working with partners in the US to introduce the technology to many more hospitals. We are providing free design support. So if you do have a project, if you do want to look what it's like, please contact us. You find all our information at avidicare.com, and through that you can get into contact us, and we will work together with you and give you all the support you need to make your successful the best possible, and also to help out towards 0 infections. Thanks. That was the presentation. I am now, we have open to questions from the audience. We have several people here in, so I will just look if we have anything here. We have one question here. It says, what impact do lights and other equipment have on airflow? Well, in general, the lights, when the air comes down, you have this turbulent zone, and that is where the bacteria gather. But if you instead do temperature controlled airflow, since the air that comes down bounces on the lamp, it will start to become turbulent. But since gravity is a stronger force, it will then take over. So the gravity will sweep down. So that's what you saw on the smoke videos, that this was really, it is a very robust technology. I have another question here. There was the most discussion regarding the diffusers. Any comments on type of return grills to use? No, not really. They have to be strong enough, and usually that's just a lint filter to get rid of any textiles. And often they're about 1 by 2 feet in size approximately, and they're situated low, close to the floor, not on the floor, like a couple of inches above the floor. That's the usual design. And there's also a question regarding cleanability of diffusers. Usually, if you have a lot of blood splatter or similar on the diffuser, you are replacing them. You just take them down, you twist it, take it down, and put in a new one. You don't have to There are no filters that you have to requalify or anything like that. You can just ask somebody in your team to bring in the ladder and do it. So since they are flushed with ultra clean HEPA filtered air from the inside at all times, there is no bacterial growth on them. There is no particular need for direct cleaning. You can, of course, spray them with an alcohol or something if you do prefer to do it, but most of our customers have measured and seen there are no bacteria, so they are not cleaning them at regular intervals. Uh, if they do using UV, for instance, they will use UV in the whole room, so they will be cleaned in that fashion. There's another question here. What is the lead time from initial order to actually receiving of delivery? We usually have 8 to 12 weeks of delivery time, depends on demand and how much else is going on in manufacturing. We have several manufacturing plants at our disposal. So lead time, we have done projects where from the first we got the request in the spring, it was delivered and installed in the fall. Whereas there are other huge hospital projects where you may start working with them 1 year and it's all only installed after 5 years because it's such a long planning process. So that depends a lot. There's also a question on installation. Well, are we installing or is it a local contractor? We have local contractors that are installing, professional local contractors. We've been working with Comfort Systems USA, for instance, but we can work with others as well that have professional installation expertise. However, what we do is that for validation, when everything is installed, we will have people from Avidicare on site, making sure that everything works as it's supposed to do. And also for the validation, measuring the CFUs if that is required. But usually we want to do that because we want to prove to the hospital that yes, it is working. Now that you're using it, it's working as it is intended to do. We have one more question here regarding clothing. Is any special clothing or any special clothing requirements? No, not really. That is one of the advantages, that you can wear your regular surgical clothing. Of course, there are requirements for clothing in any operating room, but you don't need to have the really tight ones that are so uncomfortable. So as you saw from the measurements of CFUs during surgery, there were many different kinds of clothing concepts that had been used during those measurements. And all of them, during all of those surgeries, we are able to keep it ultra clean. But of course, you can't dress like anything. You need to take some care, of course. Do we have any more questions here? There's one question here regarding pricing. Is the pricing different to classical laminar airflow systems, I suppose? I mean, well, pricing for an Operagon system, a temperature control system, is very similar to like a clean suite laminar airflow system. It's very similar numbers. So you can compare them straight off initially, and then we'll of course work with you and with the MEP design firm, engineering firms, to put together a proposal for your hospital, or if you are the consultant, we work with you, and we make a joint proposal for what air handlers are needed, what equipment are needed. But it will be nothing new to you. It's very straightforward. We've done this in so many different countries now, also in the US. So we will give you all the support to make sure you are able to get the great technical design at the right price. I can see now that we are approaching our end time. unless there are any more questions, I would like to thank you very much for joining us. Hope you had an interesting time here, that you learned some of the new things, and that you really know that we can do so much better when it comes to handling the air within healthcare. And we do have a technology that is here. It's well proven, both scientifically and in clinical practice. And we're really eager to help you in your projects so you can help your customers make a better job and avoid those terrible infections. By that, thank you very much and have a continued great day.